Welcome. Welcome to this talk, linking STEM and HASS in hydraulic engineering. And I will start with some acknowledgement of Duncan, Sarah, Michael, William. I'm a professor in hydraulic engineering, and I've been working in several interdisciplinary projects worldwide, mostly because of my personal hobby or interest into history and archaeology. But first, what is hydraulic engineering? Hydraulic engineering is the science of water in motion and its interaction with the surroundings, interaction with the sediment at the riverbed, interaction with the atmosphere at the free surface, interaction with aquatic life through the water column. And one of the most challenging aspects of hydraulic engineering is a very broad range of relevant time and length scale. If we look, for example, at the current floods in the Diamantina River in Western Queensland, the flood may last 2 to 3 months, but the turbulent dissipation takes place typically at a time scale of less than 1 millisecond. In the Australian context, hydraulic engineering is even more complicated, in my opinion, because of the extreme hydrological condition, very hot temperature and long recurrent drought. The millennium drought at the beginning of the 21st century, the Federation drought at the end of the 19th century and early 20th century. And people in remote Australia continue to talk about the Federation drought. On the other hand, we may experience extreme rainfall over a duration from 10 minutes to several months, which in turn lead to massive surface runoff on large floods, with rainfall amounts on maximum flood discharges that are world record, according to the World Meteorological Organization and the International Association for Hydrological Science. Thus, hydraulic engineers in charge of designing hydraulic structures are facing a conundrum. Hydraulic structures are absolutely necessary to harvest water reserve for both drinking water and food supply. Equally important, flood protection and flood control through diversion of the floodwater or storage of floodwater in reservoir. But possibly the less recognized contribution of hydraulic structure is transportation. You may think of fluvial transportation, like at the beginning of the 20th century, but I'm talking today about land transportation. Every time you take your car, you take a train, you take a bus, you will pass over streams, you will cross stream for bridge, culvert, causeway, which are all hydraulic structures. And thus, hydraulic engineers are facing a conundrum because hydraulic structure potentially may impact adversely the catchment through some interruption on sediment and debris supply, as well as aquatic life and fish passage. So in the next few minutes, I will share my fascination for one type of Australian indigenous structure, the rock fish traps. I'm aware that there are many types of indigenous fish traps, and there are rock fish traps in coastal zones, but today I shall focus on permanent rock fish traps in inland waterways. Structures that were fascinating because they were dealing with on a very broad range of water discharge, from droughts to mega floods. They were typically built with a horseshoe convex shape, rounded at the upstream end, open at the downstream end, a design that led to a reduction of debris trapping on fish attraction. They were typically built out of stone that were keyed together without mortar or clay. That is, where they were porous structure, and this porosity was essential to sustain the force of the current and to prevent sedimentation and siltation. Their primary role as fish trap would have been successful for a range of river depths from 0.2 meter to 1 meter. For less than 0.2 meter, the fish would not swim there because it would be too dangerous, they will injure themselves. And for more than 1 meter in water depth, it will still be unstable, too dangerous for people to fish. So in turn, this structure had obviously some secondary role. At low flow, that is for a river or water depth, less than 0.1 meter, they will have acted as freshwater reserve, possibly at water hole to attract animals and become hunting grounds. And for very large flow, typically more than 0.5 to 0.1 meter, they will act as large roughness, totally submerged and contributing to turbulent dissipation. A role which in turn will enhance the downstream water quality and the downstream sediment mixing. Interestingly, at one side, the strip, Vulcania, the fish traps were located on one side of the river section, leading progressively over the last 60 years to a deepening of the main channel. With this in mind, I undertook some simple hydraulic modeling of such Australian indigenous rockfish trap, using physical modeling in laboratory based upon the fraud similitude on 1 to 10 to 1 in 20 and distorted geometric scale. We are using generic shape, and we are still in the early stage of the project, working on the range of submergence ratio from 0.1 to 6, where the submergence ratio is the ratio of the upstream water depth to the fish trap height. So let me show you some preliminary results in terms of visual results. This video shows a typical situation where the upstream water depth is about the height of the fish trap. That will be a situation where the structure will be used for fishing. And by injecting dye through the porous structure, we see the wake as well as the bleeding through the porous rocks. The next video shows a very shallow water flow, an upstream water depth about 0.2 to 0.3 times water depth. And we see some interesting flapping of the dye downstream with the flow from the left to the right. This flapping is called a vortex shedding, and what you see in front of you is a Kármán strait of vortices, a fascinating flow. For very large flow, on the other hand, when the structure is completely submerged, visually from outside, we don't see the structure anymore, but as you can see through dye injection, it contributes to fairly significant turbulence and turbulent dissipation around and downstream of the structure. So coming back to the focus of this talk, linking HASS and STEM in modern world application, I find the Australian indigenous rock structure fascinating because they are smart hydraulic engineering structure. They require obviously a fair amount of expertise and experience in their design. They were structurally sound. They were able to prevent the trapping of sediment and debris, and they were contributing to attracting fish and assisting upstream passage. Thus, the expertise that were developed with the structure potentially could be applied, in my opinion, to modern stream crossing, the French causeway, as well as water diversion in inland waterways, particularly in remote Australia, like Western Queensland, where we have very little information on the hydraulics and hydrology of the system, as was experienced during the construction of the first Montasa railway line that you see on the bottom. Thank you very much for listening to the presentation, and thank you very much for watching.